A star vanished mid-sky, no flash, no smoke, just gone. Astronomers still caught it, using ripples and shadows instead of light. The immediate takeaway is simple: we detect darkness by its fingerprints. Think gravity bends paths like glass bends a stray beam. When something hides, its pull still sculpts the space around it. Tiny particles whisper too, leaving faint marks in strange places. We read those marks and the picture appears. Across this episode, we tour the tricks that reveal the unseen. By the end, darkness will feel almost loud. You stare at a galaxy cluster and arcs bloom around it. That warping is gravitational lensing, where mass bends passing light. It lets us map invisible matter, even when no star shines. Mass curves spacetime and light follows the curved path. Background galaxies stretch into arcs, sometimes forming near-perfect rings. The pattern encodes a map of all the mass present. Astronomers invert the distortion and reconstruct where gravity hides. The bullet cluster gave a shocking split screen of the cosmos. Hot gas slammed together and slowed, glowing in X-rays between galaxies. But the lensing map peeked away from that glow, offset by hundreds of thousands of light years. Most of the mass sailed through, like ghosts, matching dark matter predictions. Here are concrete numbers to anchor this picture. The cluster spans millions of light years and weighs about a quadrillion suns. Yet the brightest gas sat apart from the heaviest gravity. So lensing turns bent light into a direct mass portrait. Picture twin laser tunnels, 4 kilometers long, crossing in a vacuum. They are interferometers built to hear gravitational waves. These waves carry news from collisions that emit no light. A passing wave stretches one tunnel and squeezes the other. Laser fringes shift by a fraction of a proton width. The pattern flips as the ripple flows through Earth. Software filters tease signal from seismic hum and quantum noise. In 2015, LIGO heard 2 black holes collide. They weighed about 30 and 36 suns, spiraling together. The chirp lasted 0.2 of a second from deep space. About 3 suns of energy radiated away, as roughly 10 to the 47 joules. The source sat 1.3 billion light-years off, far beyond any telescope reach. Net result: ripples measured locally expose black mergers that glow nowhere. Under Antarctic stars, a cubic kilometer of clear ice waits. It is a neutrino telescope, listening for near massless ghosts. Neutrinos escape dense engines, carrying unfiltered directions and energies. A rare neutrino strikes an atom and kicks a charged particle. That particle outruns light in ice and leaves blue Cherenkov cones. Dome sensors watch the glow, triangulating tracks through frozen darkness. Catalog directions point back to energetic, hidden accelerators. In 2017, a 290 tera-electron-volt neutrino arrived. IceCube traced it to a flaring blazar, called TXS0506+056. Space telescopes cross-checked a flare, confirming a multi-messenger hit. Only one particle spoke, yet it named the culprit across billions of light-years, so a single streak in ice can indict a dark engine. A steady star twitches while its light dims by a hair. Planets reveal themselves by wobble and shadow, not by glow. These hints let us count worlds and target atmospheres for life. Gravity makes the star orbit a tiny circle, shifting its color. We read a red then blue shift, as meters per second on spectra. A passing planet also blocks a slice of starlight, like a moth. Repeated dips set the size and year, locking the orbit in. 51 Pegasi b tugged its star, by about 56 meters per second. Kepler watched hundreds of thousands of stars, finding thousands of worlds. A hot Jupiter can drop brightness by 1% every few days. Earth around our sun would wobble only 0.09 meters per second. Bottom line, tiny wobbles and dips sketch planets that never shine. Near our galaxy's heart, a star loops fast around emptiness. A black hole reveals itself by the orbits it commands. Measuring mass and spin here tests gravity, where it runs wild. Infrared cameras track stellar positions through dust near the center. One star, called S2, completes a loop every 16 years. At closest approach, its speed peaks near 8,000 kilometers per second. The path shows relativistic precession as space itself twists near the hole. Those motions weigh the central monster at about 4 million suns. The Event Horizon Telescope even outlined its shadow against glowing gas. That ring spans around 50 micro-arcseconds seen across the galaxy. No surface shines there, only gravity fences light into an orbiting crescent. So orbits and silhouettes confirm darkness where mass wins completely. Far from a galaxy's glow, stars still race around the disk. Dark matter is extra mass that emits no light at all. Without it, galaxies would fly apart and structure would unravel. Newton gives a speed limit, falling with distance from visible mass. Yet observed speeds stay flat, refusing to drop at the outskirts. An extended halo of unseen matter deepens gravity across the disk. Simulations add halos, and galaxies then hold together for billions of years. Andromeda's outer stars zip near 250 kilometers per second, far out. That speed demands a halo weighing several times the shining matter. Clusters require even more, matching lensing maps across huge scales. Direct detectors on Earth stay quiet, yet the sky insists on mass. So steady rotation writes a signature, pointing at an invisible halo. Millisecond pulsars tick like cosmic metronomes across the sky. A pulsar timing array is a galaxy-sized gravitational wave detector. It opens a window on black hole pairs, merging in slow motion. Passing nanohertz waves stretch Earth to pulsar distances, subtly. The arrival times shift by tens of nanoseconds in correlated patterns. Dozens of radio dishes log pulses for years, watching the drift. A background hum emerges from many giants across the universe. In 2023, teams reported a common spectrum process with spatial correlations. The dataset spanned about 15 years, using scores of pulsars. Signals favor supermassive binaries, orbiting with year-to-decade periods. Each contributes a whisper, adding up to a measurable rumble. So clock jitters across the sky sketch giants no telescope sees. A lonely star brightens smoothly, then fades back to normal. Microlensing is gravity acting as a lens without forming arcs. It reveals rogue planets and dark remnants drifting between stars. An unseen mass aligns with a background star, focusing light briefly. Brightness rises symmetrically, with no color change or spectral lines. Event duration sets the mass and speed through simple lens equations. Short spikes hint at planets, nested within a heavier lens. Surveys like OGLE and MOA watch millions of stars nightly. Typical brightening can reach several tens of % over days. Some events last only hours, pointing at Earth mass wanderers. Even isolated black holes show months-long curves with subtle parallax shifts, so a quiet bump in a light curve betrays a hidden body. That vanished star at the start was never lost after all. Its gravity, particles, and ripples shouted, once you knew how to listen. We mapped mass with arcs and heard collisions shake our planet. We chased a single neutrino and fingered a blazar across time. We weighed planets from wobbles and timed pulsars as galaxy clocks. We traced dark halos by the stubborn speeds of outer stars. We even caught wanderers by the clean curves of microlensing bumps. So the picture is clear, darkness is measurable and loud. If this changed how you picture the sky, join me again.